So it is my great pleasure to introduce Professor Nathan Kutz, who is moderating this panel. Nathan is the Robert Bowles and Yasuko Endo Professor in the Applied Mathematics Department here at the University of Washington, where he is also the former department chair. He holds a Bachelor of Science in Physics and Mathematics from UW here at the University of Washington, and a PhD in Applied Mathematics from Northwestern University. His research interests include numerical methods in scientific computing, data analysis and dimensionality reduction methods, dynamical systems, and I am actually going to abbreviate here a little bit and just say a long range of applied mathematics and numerical tools for doing a variety of applications. In particular, today, he's going to run a panel on data science for, ideally for satellites, or how satellites hook into it and what do we do with the data. So he has a great group of people here. And Nathan, I'm going to pass the panel over to you to introduce all of them and have your presentations. Thank you.
Great. Thank you so much, Christine. Hopefully everybody can hear me just fine. So welcome everyone, and thank you for coming. And I'm especially thankful for the panelists here. You'll see why I put these panelists together. And in fact, what we'll do is I'll give a brief intro for them in a moment. But to some extent, what I want to do is highlight the overall architecture of what we want to think about in the modern world. And so I'm going to go ahead and do a share screen here and share one slide. And I just have one slide to kind of walk through a little bit, which is in many ways what I think about of where we are in 2023. Although there's so much talk about machine learning and AI and how that's going to be integrated across science, in my view, the real star of the show is sensors and sensor technologies. I think that's what's actually driving everything. And if it weren't for the sensors, machine learning wouldn't function. It's the quality of data, what we can do with data, that's really driving and accelerating our ability to do scientific and engineering discovery. And it's across every field, right? You look at what people can now actually measure on the brain in biology and neuroscience, all the way to what we're talking about now, which is monitoring of space and remote imaging and so much remote sensing, and so many different modalities of being able to bring in massive amounts of data. And of course, that's this input layer here. So this picture really represents this idea of a paradigm, which is we're going to bring in massive amounts of input data. And part of our objective is to first figure out what kind of data can we bring in today. And so this is partly why Greg Hegum, professor in atmospheric sciences here, we're going to talk about what are people being able to do now that they have never been able to do in terms of recording data and the access that we have here to the data. But from that data, you want to bring it into and start learning from that data. And so we have this pipeline that I call here coordinates or representations, learning how to think about the geometry of this data or the space of this data. And also, maybe instead of just ingesting this giant pipeline of data, maybe we should think cleverly about where should we be listening to the most important pieces of data. And so this is where we move to Krithika Manohar, professor in mechanical engineering, where Krithika has really done a lot of exceptional work in thinking about how to use your sensors in the best way possible. Maybe you can even use fewer sensors. In fact, that's one of her things that she has shown is if you listen to the right places, you can still get just as much information than listening to this giant pipe. Because there is this issue of maybe we have too much data, but what's the data you should be listening to? And finally, once you actually collect this data, learn how to listen to the data, you now have data itself that you want to start building models. In other words, a lot of what we tend to build are physics, geophysics, biophysics inspired engineering physics type models. Once we bring that data in, how do we build models rapidly? We are used to in our development pipeline overall, from what we have, in our classical education system, we learn a bunch of physics, we learn models in physics, and we typically build our models from first principles upwards. But now, with the data we have, with the abilities that we have, especially with machine learning tools, we can now build models directly from these data streams, especially models that are interpretable and manageable. And this is why Urban Fazell is on this call as well. So Urban sits at this interface of bringing in data and has one of the best techniques out there for learning dynamic models, governing equations that are getting at right at the intrinsic evolution dynamics of what the process you are measuring. So the way I think about it is our speakers represent, in some sense, the entire pipeline, from taking the data in to figuring out how to use that data and then building models to that data. And then you can do things like prediction, estimation. Some applications you can even do control. That's typically not something maybe you could do with atmospheric dynamics, but there are many other things you can actually thinking about. If I get good models, I can control them, and forecasting and things of this nature. So a lot of us have different reasons why we want to build the models. Usually they're either monitoring technologies, or they are actually some kind of actual product we want to use to be able to do scientific discovery. And what we have here in the panelists is the entire range from input to output, the entire pipeline that you need in place. So that's why these three panelists are here. Each panelist is going to give a little overview of some of the ideas that they have here around these three pieces. And so the way this is going to work, they're each going to start off with a little 10-minute, here's sort of the state of the art. And then we'll move to each panelist, and then we'll open it up to broad conversations from you guys. So think about the questions you might have, but this is a real opportunity for everybody to come in and ask questions from the panel, from this group of panelists here, because I think what we have is the representation of this end-to-end pipeline of what we want to be doing with data. So with that, I'm going to start at the left end of that pipe and move to the right. So we're going to start with Greg, and then go to Krithika, and then go to Urban as we do this. And so for each, I'll give an introduction here. Actually, maybe what I'll do is I will let each one talk, just maybe give a little bit of background about what they do, and then talk about their slides. So let's go first to Professor Haycomb, Greg Haycomb, out of the Atmospheric Sciences Department. So Greg, take it away. You can maybe do a little intro for yourself and show some of your slides.
Yeah, thanks so much, Nathan. It's a pleasure to participate in this panel discussion. So I am a professor of atmospheric sciences at the University of Washington. I've been here for 24 years. I served as department chair for 5 years. And broadly speaking, my research interests are in fusing models of the atmosphere and the Earth system generally with observations of the system. And I've applied what we call data assimilation, and I'll talk briefly about that in my little overview, to problems ranging from convective weather events that happen on the timescales of seconds to minutes to paleoclimates that occur on timescales out to the last 55 million years. So the same general techniques apply. So Nathan, can I do a screen share and try to get my slides going here? All good? Yes, excellent, thank you. Okay, so go into full screen mode. So just a brief overview of what I'm going to talk about. I'll give you some background on how space-based observations fit into the mix of how we use them for weather and climate analysis and prediction. Data assimilation is this activity that I just mentioned, how we fuse these two things together, accounting for their errors to optimally estimate and predict the state. The key part of this is going to be the forward operators. And for space-based assets, that is, we're basically measuring radiances in space or other quantities. Could be a return from a LiDAR or a radar. And in data assimilation, we need to compare those two things, an estimate that comes from a model and an estimate that comes from the sensor in space. And then with all of that warm up, I'll tell you what I think the most recent trends have been. Like every other field, it's extremely fast moving. And what I saw in a meeting a couple of weeks ago in Europe was different than what you will see in the literature just coming out today. So it's really fast paced. So just in general, these space-based observations are essential. They are the backbone for weather and climate analysis and prediction, also for what we call reanalysis. And these are these globally gridded multivariate data sets that are the foundation for climate studies and incidentally for training machine learning models. There's a wide range of constituents. We have government agencies active in this area. I'll talk about the European Center. Here we have NOAA in the United States. The military is actively engaged. As all branches of the U.S. military have their own activity in this area. Private sector firms have really bloomed in the last 10 years, and of course, academic institutions. So just to put some context on this, going back to the early 1980s, this shows you one measure of forecast skill from the European Center. And if you focus on this blue line right here, you see that it's trending up toward higher skill over time. The dark blue line shows you the skill in the northern hemisphere, and the light blue line shows you the skill in the southern hemisphere. And there was a big gap that started to close, and these curves jumped up around the year 2000. And that was the time when we figured out how to use satellite assets. Before that, we had to use basically in situ observing assets. And of course, there's a big skew toward the northern hemisphere because the population of Earth is biased that way. And the other curves on here show you at different forecast lead times going out 5, 7, 10 days into the future. We're now getting forecast skill, for example, at 7 days, as skillful as we had 20 years ago at 5 days. So the observational assets, it's just a massive pipe that we have constantly streaming in observations. We have these in situ assets that I just mentioned, and then we have the space-based assets. And if we look at what fraction they constitute and what is used for analysis and forecasting, where you see the red and the pinks on this pie chart, those are all space-based assets. So it's more than 3/4 of the observations are coming from space. And there's nearly 1 billion of these per day, and about 60 million of those are quality controlled and assimilated. So this is the other side of the coin that I think Krithika will talk about, which is in addition to optimal sensor placement, you could talk about optimal sampling from a big data hose and plucking out the needles from the haystack. So data assimilation involves a combination of information from a forecast that came from previous observations. That's the blue line. That's our prior estimate. And if we have a forward operator that can take us from that state, whatever the model has in it, to these observations, and we have error estimates for both the observations and the prior, we can go through a minimization process, variational or classical Kalman filter, if that's the way you want to think about it. And we basically get an adjustment to a new state, which is given by the red line, which produces, when we launch it into the unknown, into the future, gives us a corrected forecast. So now the question is, we can answer this quantitatively, what observations have the biggest impact on that forecast skill? So that's what you're looking at here. And there's two different ways to estimate how important these observations are. The blue lines and the gray bars, doesn't matter. Those are just two ways of doing it. The important thing is the height of these bars is biggest inside this big red box. Those are the satellite assets. The in situ assets are on the right, right? So most of the skill that we're getting in this forecast is coming from satellite-based assets. Now, if you weight this on a per observation basis, because these satellite assets are so abundant, then you find that the in situ assets are actually more valuable on a per observation basis. But if you think about it on a cost basis, as the cost of gathering these space-based assets plummets, I think this is inevitably the way things are going to go. And the in situ assets, I think, will have to fight for survival. I can just breeze through this. I have a few slides on some of the tech. There's many, many of these observing strategies. Passive microwave is a big one. So observing at different frequencies, just the emission of radiation coming up from the atmosphere to satellites that gets measured at different frequencies. There are weighting functions with each one of those channels. We can then do an inversion and get temperature distributions across the entire Earth from a whole array of these geostationary satellites. We can forward operate on these from the model states and then do the data assimilation that I just talked about. GPS occultation is another really important one, provides super accurate vertical profiles of the atmosphere, including ion density up in the ionosphere, vertical profiles of temperature and humidity. So basically, this is just piggybacking off the GPS network. If you put low-cost receivers in space, all I have to do is measure the signal delay from the GPS transmitters or observe the bending angle as the signal is refracted through the Earth's atmosphere, and that reflects the constituents that have contributed to the delay or the refraction through the atmosphere. So on the left, you see these cover the entire Earth as compared to in the red, that's the in situ observations from balloon observations, what are called radiosondes, which we've had as the backbone for the observing system since World War II. So these are much more abundant and they're globally distributed. We have cloud motion vectors. So we're observing the atmosphere so frequently from space down to minutes now from the geostationary satellites. We can track individual cloud elements. We can determine their elevation. And then from that, we get the motion of cloud elements, which tells them that the wind that's carrying those clouds. So the forward operators are a key part of this activity. There are two main code bases, RT-TOVs, mainly used by European agencies. So again, these are simulators that will predict, given the state of a numerical model for the atmosphere, a physics-based model or a machine learning-based model, what's occurring up at the satellite. Now, these models have huge bias. The bias is leading order. It's bigger than the innovation. That is the difference between the short-term forecast and the observation. So a lot of effort goes into dealing with that bias. And in fact, this is my last slide, just to set up where I think the machine learning, a lot of the ferment is happening, has been on these forward operators to develop fast forward operators to approximate these expensive ones. You can go all the way down to line by line, laboratory-based estimates of the spectroscopy of the absorption profile of the gases and the other constituent in the atmosphere. These forward operators are simplifications to that, but they're still expensive. And so what people are doing is developing machine learning based operators that are much faster and provide the same level of skill. People are also looking at how to update the unobserved variables. So if you think about the Kalman filter, the Kalman gain gives you this link. It's a covariance in terms of at the level of the Gaussian statistics, the Kalman filter. People are also experimenting with purely data-driven weather forecast models, which we spent the past 50 years developing these physics-based models. But just in the last 6 months, there have been 2 of these models, one emerging out of NVIDIA, the other one out of DeepMind and Google, that are now meeting or beating the very best government-based operational weather forecast systems in the world, and they're completely data-driven. Now, what has not happened yet, but is something that I'm very interested in, is the prospect for, as Nathan hinted at, entirely observation-based models that don't use these reanalysis data sets, but mine these satellite observations by themselves. So models that are encoded just to predict that, and then to have it decoding or downscaling to the other variables that we care about as humans for predictions, that is wind, pressure, precipitation. So I think that encoding, decoding paradigm is liberating in the sense that we don't necessarily have to put everything in there that we have traditionally into our physics-based models. All right, I'll leave it there. Thank you.
Thank you, Greg. So as you can see, what Greg has actually set up for us is this, the data pipe that's massive, and it's almost right. We have to actually think about that a lot. I mean, one of the things we always talk about in machine learning, and it's like, oh, just take the data, but it's like this is a level of data that is so enormous that we have to think about how to use that effectively and how to come in and say, okay, we want to do this in real time. One of the advantages of being like at a Google or DeepMind, you can just go throw your things on thousands of GPUs and not worry about the cost. But for most people, that's just not realistic, or even, right, this is exceptionally expensive. So what we're going to do is move to Krithika Manohar, professor in mechanical engineering, who is going to really start getting us to think about how do we listen to data more carefully. Once we have these data pipes, what are the key pieces that are going to allow us to have the most information? And even Greg already hinted at this, right? People are thinking about this. And how do we build techniques to really mathematically justify what we do in that sensor optimization, sensor placement, sensor listening? So Krithika, please take it away.
Thank you, Nathan. Thanks for the opportunity to participate in this panel. So I work in the space of machine learning, physics-informed machine learning and AI tools. whether that's computational tools, theory, or algorithms for aerospace engineering and other complex engineering processes such as nuclear and atmospheric sciences as well. So just to give you an idea of some of the applications I work on, let me start sharing. Okay, can everyone see? Perfect. So you can kind of see some of these examples of real-world applications of physics-informed ML and AI on the bottom. I will talk about some of these, and in particular, the unifying thread for them in my work, which is optimal sensing and optimal sensor placement, particularly in regimes where sensors are limited and sensors that stream real-time or very high fidelity information or in situ sensors as well. I'll also talk about some applications in aerospace manufacturing. So these are considerations in how you might actually deploy satellites and build these tools from which you do remote sensing and have space observations. Okay. So one of the main challenges in these limited sensing scenarios is that you might have constraints on the number of sensors, the sensor capability, and operating conditions in your flow may be hostile to sensors. In atmospheric applications, these may be buoys in the ocean that stream like surface measurements and other things like that. Oftentimes, the optimization of sensor placement is a non-convex NP-hard optimization problem. So what does that mean? Oftentimes, you look at a number of candidate locations for sensors. You might have N candidate locations, and you have a budget of P sensors. Determining the optimal placement with respect to many objectives that we see in control and inverse problems and flow reconstruction is N choose P. So that's combinatorial complexity. So that's, you can, for some of these applications where you have 90,000 grid points in a simulation, or spatial grid points or spatial locations, just enumerating the possibilities is almost more than the number of particles in the universe. So that's computationally intractable. However, we can exploit physics that we learn from data and dimensionality reduction and pattern extraction tools to come up with greedy algorithms for sensor placement that are very close to the optimum and in sometimes provably close to the optimum. And we can do uncertainty quantification with respect to the things like the error covariance that we expect with filtering and other optimization algorithms. So when we come, my general pipeline is we have high fidelity data that we might have from simulation and modeling, and we do dimensionality reduction to reduce the search space for this design problem on top of whatever optimization we have, which is choosing where to measure or where to deploy observations for our downstream task. So I'll give a couple of examples in aerospace manufacturing. These are collaborations with Boeing at UW and in the Boeing Advanced Research Center. One of these is to reduce the measurements we need for shimming large-scale composite parts. Of course, these are necessary for remote sensing applications and satellites and so on. The goal here is to basically reconstruct gap distributions that occur between large-scale composite parts, such as the wing-to-body join. And it turns out with the optimal sensors from our methods, you can reduce the number of measurements of these gaps by 30 times and still reconstruct these gap distributions with 99% accuracy. This is important because these gap distributions cannot be modeled from first principles. You have to be able to build the models from historical data of these gap distributions to be able to predict what these measurements should be for new aircraft. On the right, we see a project where we try to eliminate the need for shims in the first place, or shims are filler components that are designed to enhance structural integrity. So in large-scale assembly, like sections of a fuselage, a lot of deformations occur before we get to the final assembly. And in order to avoid the need for shimming in the first place, we want them to meet a nominal shape. Here we have an optimal actuator placement problem where we have a sparse number of actuators around this assembly, this enormous assembly of a fuselage. And we want to apply these motored movements to deform the assembly to meet a nominal shape. So it turns out this is a very difficult problem, but we have tackled it using these data-driven methods and a combination of modeling, simulation, and actually gathering data from a test rig that we have at the BARC right now. And similarly, we may have other constraints on sensors, such as they have to be non-intrusive. These show up in ergonomic risk monitoring applications in the final stage of composite manufacturing or composite layup. So you want to be able to combine data from multiple sources in order to be able to predict some target quantity with very high fidelity and precision. So these are some of the different areas in the pipeline where optimal sensor placement and optimal sensing really has a huge potential to have an input in the design stage of these assemblies and basically optimize these processes and streamline them. Another important application that we're working on is digital twins, which you can think of as a souped up suite of physics-based simulations and reduced order models that are designed to communicate with the physical space or product through sensors. So here, sensors link the digital and physical spaces. And a digital twin is important where you cannot necessarily test failure modes physically, for example, in nuclear reactors or flight testing. So here, optimal sensor placement becomes really important because we don't necessarily know the operating systems from when this fuel rod prototype is deployed into a reactor, for example. This is a very hostile environment, and the small number of sensors that you can place have to be placed carefully so you can estimate the thermal hydraulics effects within the reactor for this fuel rod prototype. So this helps optimize the number of sensors we have for control, for remote monitoring, and for enhanced safety of these extremely dangerous processes. So this is a collaboration with Idaho National Lab. We're deploying sensors into this twist capsule, which is a prototype of a nuclear fuel rod, so that we can learn about thermal and hydraulic behaviors. So basically reconstructing temperature fields and things like that without actually testing it on a physical prototype, and start this cascading neutronics effect, which is extremely dangerous, as we all know. To summarize, there's a huge potential to leverage the tools of optimal sensing for these space and satellite applications, and in particular to combine the tools of optimal sensing with things like data assimilation and reanalysis for weather forecasting, climate forecasting, and estimating ice flows and so on. So with that, I'll turn it to Nathan and Urban, who will also talk about, constructing the data-driven models based on these sensors.
Great, thank you so much, Krithika. And so you can see that, so part of the goal here with Krithika is again, in the engineering process and quite a bit of work in the aerospace industry is to think about how do you make the best use of data and listen to things. And also a very interesting paradigm that we're going to come back to, and I think in the discussion, which is the idea of a digital twin, right? Which is I have a model and I have data. I would like these to be similar so that when I run my model into what if scenarios that have some confidence going to look like the real world, and it plays out across the engineering physical sciences, whether we're doing control or not. And so, you know, there's clearly this development of a digital twin for weather, right? Even though I don't think that's what they would call it. But now, yeah, they do. Okay, Greg's saying it maybe. Okay, yeah. And now the interesting thing is we're going to move now towards, now that we're collecting the data, what are the possibilities and prospects for turning that data into, let's call it, human interpretable models? In other words, can we boil this down? Can we use machine learning architectures to give us models that we can start thinking about, like, oh, I see what's happening, versus the possibility of just building black box deep neural nets where you don't have any access to understanding what it did. We want to keep focus on, if we're going to drive science forward, humans are an amazing extrapolation tool. Humans are amazing at positing new technologies, but we first have to have core understanding. And this is where I want to turn to Professor Urban Fazell at Imperial College London. Thank you, Urban, for joining us from he could be at the pub now, but he's here. It's a Friday night, but he's here with us. And so thank you for coming. And he's going to tell us a little bit about some of these prospects of what we can do with data.
Yeah, awesome, Nathan. Thanks very much for this kind of introduction, and indeed craving for the first pint, but I have another 45 minutes patience, I think. So yeah, well, my background is not exactly in space, but more in aeronautics. So I'll start with a quick overview and introduction of my main work, but ultimately what I'm going to talk about is dynamical systems that we try to control or learn their unknown or unmodeled dynamics, and that's definitely also fairly or very much applicable then to other fields such as space, etc. So yeah, what you see here on this first slide is basically an overview of my main interest in aeronautics. I'm mainly interested in designing and controlling morphing wings, so flexible structure that flexible aero structures that can basically adapt their shape to different operating conditions and thereby optimize their performance. But for instance, on the left here, you see one example of a carbon fiber additively manufactured morphing wing that can change its camber over the full span of the wing. And then in the center video, you see a second wing with a similar concept that we apply to this drone that is used for energy harvesting. And the main optimization or the main motivation behind these systems is basically found in nature. So when we think about birds, they have this incredible capability to adapt to different operating conditions. So for example, when we think about a falcon in its like standard configuration, like high aspect ratio, it can very efficiently glide, but then within no time crack its wings in, dive down, and perform this prey maneuver. So it's super impressive how these birds can basically morph their shape and optimally perform over these wide ranges of operating conditions. Now, what we are interested in is basically mimicking these morphing capabilities, but there are three main challenges to basically achieve these morphing capabilities. And the first one is design of these systems. So how do we actually find an optimal design that actually improves the overall flight performance of a flight system? Second is manufacturing, and third is control. I won't talk a lot about manufacturing. There's lots of progress now being done in additive manufacturing. So for instance, the wing on the left, we use a lot of additive manufacturing capabilities. But in terms of design and control, we make a lot of use of recent machine learning methods to basically enable control and design optimization. So in terms of design optimization, this is a fairly application specific problem. So the main application that I'm interested in is, for instance, this airborne wind energy. So a wind energy system that is using kites to harvest high altitude winds. So that is basically also the prototype shown in the video here in the center. And on the right, you can see a model that basically simulates the coupled flight dynamics and also fluid structure interaction of these wings. And we can see that these systems are high dimensional and fairly like multidisciplinary, so coupled flight dynamics, aerodynamics, and structures. We can build these first principle models, but the problem with these models is that they are extremely heavy. So they're not exactly useful for control because they run way too slow, and they're also not very efficient for design optimization. So basically, in the next two slides, I will present two methods that can be very useful for design and optimization, where we can basically learn models that can be applied for these particular problems here, but that also have other potential applications in fairly different fields that we'll see on the last slide. So the first the first example that I basically want to talk about is this data-driven control method, where we try purely based on data to find these best fit linear models that can be used for control. And I think a technique that Kritik also already showed in her slides, or a similar method, is this dynamic mode decomposition with control. So basically we collect a set of snapshots. So for instance, in this case here, pressure data on the wing, but that could be all sorts of data. And we build these state space models that can then basically be used to predict the future state of our wing, considering these particular morphing inputs. And we can apply these data-driven models now for extremely fast control. So for instance, what I show here is a dynamic mode decomposition model that is used with a model predictive controller for gust load alleviation. So basically what we can do with these models is extremely efficient and fast control. And what we show basically in our work is that by using these data-driven methods, we can push the limits of our operation of the wings towards higher loads and therefore maximize the power production. So using these data-driven control models can actually improve the power production of these airborne wind energy systems. So that is one super exciting data-driven modeling strategy. But in this morphing wing case, what we basically do is to find these best fit linear models. But for many systems, these linear models, of course, fail to accurately represent the dynamics. So what I show here is an ongoing collaboration that I actually started during my postdoc at University of Washington, so a year ago. So what we see here is this flapping wing robot that was developed by a group at MIT, which is another very interesting flight system that includes these flexible wings that are extremely challenging to model. So, for instance, what we see here is this flapping wing performing this circular maneuver, which is possible to do with these initial linear controllers. But when we want to move towards a more dynamic operation, we basically need more accurate models, especially of the aerodynamics, that we cannot derive with first principles for these particular systems. And that's where we basically start using data-driven models that can learn governing equations. So not like in the slide before, where we tried to find these state space linear models, we are developing model discovery techniques where we can ultimately learn the underlying physics when we perform these fast maneuvers. So the approach here is very similar to the dynamic motion composition, where we collect basically data and then also perform a sparse regression to find these unknown dynamical systems that are then basically interpretable and that can be used for control. And I think because this is a seminar at the University of Washington, I won't go into detail with the actual algorithm that was developed at the University of Washington by Nathan and Steve Brunton and collaborators. But ultimately, what the problem with these algorithms is that they're fairly, they might not perform very well with noisy and limited data. So in our recent work, we basically extended this algorithm and combined Cindy with ensemble learning to make these model discovery methods more robust to noise, especially in the low data limit. So our ensemble Cindy method is now basically able to identify these models even from fairly little and noisy data. And the main idea with these models is now to basically apply them to first better understand these unknown dynamics, but we can also use them for surrogate models, for instance, in design optimization. So one of the main challenges with morphing wings, but also in reinforcement learning algorithms or other type of applications such as active learning. So how can we most efficiently collect data to find these models with the least amount of data? So lots of opportunities with these data-driven model discovery methods. And I was mainly talking about aeronautics problems, but I think there's also lots of other application opportunities for these type of models. So I'm very excited to discuss how we can more broadly apply this method also to satellite systems and how we can connect it to the ideas of Greg and Kritika.
Great. Thank you, Urban. Okay, so now that kind of gives you a broad overview from data collection, sensing, to model building. And I want to then open this up as the panel, right, for people to just ask questions. You can either ask them directly in the chat. Amy, what's the best way this is to work if people want to ask? Or if
Yes, so they can go into the Q&A in Whova, and we currently have one question there.
Perfect.
Should I ask that one?
Sure, please. Yes.
Okay, so for Greg, with access to space getting cheaper, are there ideas for new space-based assets which can give us more helpful data? Or is it mostly a problem of using the plentiful data we already have effectively?
Yeah, that's a great question. So right now there are private companies doing things that would require full state support in years past. There are a number of companies putting up these CubeSats, these low cost, low Earth orbiting satellites to do custom sensing for a wide range of applications. So there's Tomorrow.io is one that immediately comes to mind. And there are a couple of others developing cheap sensors, and this low cost access to space now is revolutionizing our ability to sample Earth and its atmosphere. So I think that's a strong trend. It will continue, and it's basically democratizing and distributing access to this data. How exactly you use it, I think, is the next important step. And I think that's the subject of this panel that Nathan's put together is, okay, we've got all these observations, now how do we use them effectively? If you have a follow-up, let me know. Or if I missed the mark, I'm happy to add more to it.
In fact, maybe I can also lay out something there, unless Amy, there's somebody else in the chat there. But let me throw out a question for us as panelists, and it's I think it's an important one in the sense of the following. If you look at what's going on in fact, I'm going to maybe do a quick screen share here. if you don't mind. So here's the question and the nature of the question. Let me just share this. So what you're looking at here is the state of the art in autonomy and machine learning. What you have on top is this amazing robot from Boston Dynamics. And on the bottom is a self-driving car. So we all know that these are sort of going to come into our overall space interacting with us in the near future. But there's a big difference between these two. And I'm going to ask this in terms of space monitoring. The top one is still driven a lot by physics-based models. So that robot knows about F equals ma. It knows about angular momentum. It knows about momentum. It knows about having to stay balanced. The bottom one, just as successful of a paradigm, it's not built on physics at all. It's banks of sensors with amazing training data. So maybe my question is this for the panelists, and this goes back to what you were talking about, Greg. Do we need NCAR? Okay, that's the controversial way of asking. And NCAR runs these simulation engines. So does the European Mid-Latitude, I don't know, I can't remember what the acronym is. The European Center for Forecasting, they're forecasting still physics-based models, but the fact is your sensors are right there and they got rich time histories. What happens to physics-based models? Do you guys have a perspective on what the future of that might look like? There's my grenade.
I don't want to dominate the conversation, but I can give you a couple of anecdotes in my perspective. So my perspective is, historically, we've had these physics-based models, but the fact of the matter is there are thousands of tunable parameters in these models. There are lots of parameterizations. We're never going to resolve photons. We're never going to resolve aerosols, dust particles, and they're very important when you get right down to it, weather and climate analysis and prediction. So that means these models are mostly parameterized. We need to fit those parameters. And that's been the challenge for the past 50 years. Then we have these data-driven approaches, which are now rivaling the physics-based models. But if people start to look carefully at their dynamics, time tendencies, and most of the time they don't, for those of us who are interested in that, you start to see funny things. You start to see artifacts. So my view is there's going to be a convergence of these two things. One, mostly physics with parameters that have to be tuned, but it's not done very well. Purely parameter-based models, so feed-forward networks or whatever it is, you got a billion parameters you need to fit with the data, but you need to bring some physics in to constrain that. It can't just be a loosey-goosey, we're going to ignore the laws of physics. These two things are going to come together. How exactly that happens, I think there's going to be movement on both sides.
Urban,
Yeah,
horrific.
I couldn't agree more. And I think I really love the example of the Boston Dynamics, where they, do everything still physics-based. They have model predictive controllers. When you build your robot, you don't necessarily need to learn its dynamics. You can just derive them. I think the reinforcement learning community pushed quite a bit towards, learning all these data-driven models for things that we actually know and don't necessarily need to learn. So I couldn't agree more. For certain things, these learning-based models will be extremely useful, but for things that we already know, let's just keep on using these physics-based models. And I think that's very important. That I love that you showed this video, because I think a lot of reinforcement learning engineers are crying a bit when they see that, oh, still use physics-based models and model predictive control for controlling these robots.
Yeah, I will echo that sentiment, because reinforcement learning agents that have been successful at playing games, for example, have been trained on 1,000, incorrect strategies. They basically cycle through trying different things and optimizing the reward function for hundreds of games and iterations before learning the optimal strategy. The trouble is in low resource, high cost, safety critical applications like optimal sensing in nuclear reactors or on aircraft or on drones. This is not always possible. You want to use the physics to learn an optimal strategy with minimal intrusion into the process, and minimal physical testing as well.
Nathan, can I give you a counterexample that I just saw recently? about where humans in the loop are important. So for these forward operators I talked about, we need a radiative transfer model for what the satellite observes and what we can model given our resolution of the atmosphere. If people just did traditional feed forward neural networks, you throw the data in the left side, you get an output on the right side, you fit the parameters, they were getting okay, not great results. But the most recent stuff I saw, people said, well, what if we start mimicking how we do this with the radiative transfer models in the perceptrons of the neural network? That is, we feed forward from the top of the atmosphere down for one path as the photons go through the atmosphere, and as they return the other way. So they structure the neural net and they got much better results. They basically can reproduce what they're getting from the more sophisticated models. So I think this, knowing about the physics of the system, not just encoding the physics somehow, can really help with building strategies and solutions.
We have a flurry of messages.
Okay. All right. Maybe you could just start reading some off and we can
Okay.
line them out to here. Homework.
Great. Okay, for everyone, given the hardware limitations on many spacecraft, what are the top barriers to developing the TRL of ML models?
Well, I will, let me just start off with one comment. I think this is such an important question, which is one of the success strategies we have seen, right? For instance, take something like, let's not even do aerospace. Let's just talk about playing the game of Go. You're right. We have AlphaGo, we have AlphaZero, both of which have shown that they can beat all the humans on Earth, right, with training. And, as Kritika said, it's based on sort of an RL type agent, but really they're playing billions and trillions of games. They're paying millions of lifetimes of games, right? You take your top Go player and you calculate how many games do they play over a lifetime. And this, and what it's assuming essentially is infinite compute power off the back end, right? This is DeepMind saying, it doesn't matter how much it costs to train this. I'll train it on, thousands of GPUs over a year or two. And then when you put a satellite in space with limited compute power and limited, computational resources, and also limited just power, right? So not just compute power, but actually energy consumption. I think there are some real challenges there. And that's partly why when we start talking about what we're talking about here, it's so important to think about which sensors we listen to carefully, because you don't have, maybe on ground-based stations on Earth, you might have the luxury of being able to just power up massive compute power and you have no energy barriers. You just say, it's going to cost me a ton, who cares? But in space, you have such limited budget. This is why I think so many of these architectures become important for us. So that's actually my little take there, is that there are massive constraints in real physics-based systems that we have to respect in terms of their energy budget and their compute budgets. That's what makes humans amazing, actually, is what we are amazing at is actually with limited energy and compute resources, we make exceptional use of them. So that's one of the things about biological circuitry. It's just quite remarkable how little energy consumption we need to make very sophisticated decisions and integration of our senses.
If I can add another perspective to that question, on the one hand, there's building physics into models. On the other hand, there's knowledge of the tools of uncertainty quantification, model validation, and discrepancy modeling that are important to use with these ML and data-driven models. So for example, in my collaborations with Boeing and Idaho National Lab, the nuclear applications, every choice of sensors we have has an associated expected error, reconstruction error associated with it. And we can look at it, look at the distributions of these error, and if in real-time operating conditions, if these validated errors start to diverge from that, we can also try and flag the process as deviating from the actual model and the actual experiments. and basically do a calibration, model calibration to reflect the process. So there's two-way communication between the sensors, the models, and the actual physical prototype.
Yeah, I think that's a really exciting point, because that's ultimately exactly what we do, for example, with these flapping wing drones. So we know their physics quite well, but as soon as we push their flight envelope too far, we enter regimes that we cannot model with these first principle or physics-based models. And that's where discrepancy modeling can kick in and, you know, improve these initial physics-based models. So that's, again, another very nice example of combining physics and physics-based models and machine learning-based models. So using data to improve models later down the pipeline.
Should I go on
Yeah.
to the next
Yeah,
question?
sure. Get us another one.
All right. What techniques, and this is for any and all of you, what techniques do you believe are most effective in generating information from data? Nothing like a very narrow focused question.
Anybody want to take it? Take it. Yep.
We can also loop back to it.
Maybe we digest that one. Maybe ask the next and we'll come back to it.
I would say maybe we could follow up and ask them, do they mean information in the Shannon sense or information in like actionable decisions by humans? I think if they could just narrow that question down a little bit, we might be able to provide an answer.
Okay. All right. Next question. With the rise of GPT and other unsupervised learning methods, how do you see humans and machines teaming together to derive sense-making and insights faster across our growing proliferation of remote sensing options? Will this introduce new biases in black boxes, or will it expand our curiosity and insight? It's kind of a magical question.
Maybe I'll start here, because I'm teaching an intro to machine learning course now. And at the beginning of the quarter, to use a more, pedestrian term, there was a lot of notes going around, the UW like freaking out about chat, coming online. Is anything you read actually written by a student, or is it just put to chat and they wrote me I just tell it to write me a 5,000 word essay. I just give it what I want and it does things. I embraced it fully, however. And so in class, I teach with it and I say, okay, so chat's going to write the first versions of any code we do. Okay, we're going to build a classifier and we want to do support vector machines. So I'll just say, chat, write me a support vector machine classifier for this data set. Within 30 seconds, usually less, out comes the code. I can go run it. So at least in my perspective, yes, there are going to be certainly issues with chat. But on the other hand, I'm finding that the process, my goal is to solve a science problem. Chat gets me to getting to the solution of that exceptionally fast. When I look at the code it produces, I say, yeah, I could produce that code. It would have taken me, whatever, a couple hours. And then I had to debug myself because, oh yeah, I forgot a colon there. Whereas chat doesn't make those mistakes and I can pretty much pop it in and I already have a rough draft of a code. I save myself a couple hours. The production cycle of where I want to go is massively accelerated with chat. And so there's a whole, growing trend towards prompt engineering. How do you get chat to give you back what you want? Which means if I ask it the right questions and the right blocks of code, I can just pull it right in. So I think it can be a critically enabling, like just in terms of rapid prototyping and development. There are issues, right? It's based upon a collection of data that is out there currently for it to draw from. And so it's just not going to extrapolate for you a new solution, but it's going to give you probably a good solution from, let's say, the corpus of I was going to say human knowledge, but the corpus of what's on the internet, right? And code base that's on the internet, and that's what you can pull from. So I think it's quite a valuable tool, personally.
Yeah, I totally agree. And to follow up on that, ChatGPT is unique in that it's a generative model. Well, it's not unique. There are many generative models. The power of generative models, despite the, there are some pretty serious concerns about, generating text and images and all that. But we can also leverage generative modeling to generate synthetic data where we don't have enough data, like classifying defects in manufacturing. Usually defects are a very small percentage of these strictly governed engineering processes. And oftentimes we need to generate synthetic data to develop more robust classification models that can actually flag defects in real time on aerospace manufacturing applications. So this is a major, I think, enabler for generative models in engineering applications. I don't know if that answers your question, but this is a side thought.
Next question.
Sure.
Okay, let's see. Another one was just upvoted in front of the one I was about to read. Hold on a sec. All right. Given that certain space applications do not produce much data or are not even executed yet, how do we use ML methods? Artificial data generated from small data sets, greater reliance on physics-informed modeling?
So the question is really the limited data and using our physics-based model to supplement it, right? I think that's the gist of it. You can take that.
Who wants to put that into ChatGPT? See what happens.
So the way I heard the question was, basically, if you want to design a sensor and put it in space, what kind of process do you need to have expected outcomes or how to predict the outcomes? And so the way it works in my world, when NASA wants to put up a satellite to measure things that are of benefit to atmospheric modeling and forecasting, they do an observing system simulation experiment. And this is where digital twins come in. You need to be able to sample a digital twin with a forward operator that mimics what the sensor will produce. And of course, it's always, you have to assume the model's perfect. And this is where I think machine learning is going to change that historical practice, is again, to strip out that bias and to give more accurate estimates of what we might anticipate from the sensor, which is always a little over optimistic with the traditional OSSC experiments.
Yes, so for example, maybe similar in aeronautics, when we develop controllers for these particularly finicky robots, like the initial models that we discover basically also use to improve our simulators, where we can then test and evaluate different control strategies. So fairly similar, we build better digital twins by using these initial flight tests, that we basically learn models to improve these simulators. I don't know whether this is exactly connected to the main space question, but at least we also perform these type of stages in robotics or flight robotics.
Maybe we can go to the next question if there's no more.
Okay. One advantage about physics models is that you can explain the why behind the phenomenon. How does this fact influence your perception behind the notion of explainable AI/ML?
Yeah, I think the nice thing about certain machine learning techniques that we develop is that we actually learn governing equations. So by performing these, or by using these methods, we can learn physics, which is, I think, extremely interesting. So we move from black box to actually white box model, discovering ODs or PDs. that we can look at. We can look at the different terms that we basically identify and have a conversation about, oh, interesting. So quadratic term in the pitch dynamics of these robots, for instance. And I assume there is lots of similar potential also in space. I don't know if Greg or Kritika has something to add.
Yeah, that also ties into methods for feature selection in these models. So you can identify the important physics, but the important features that contribute to those physics can tell a lot about the process. So, for example, if you're trying to characterize defects in manufacturing or automated fiber placement, we need to know like what are what basically causes these defects so we can try and suppress them. Is it the geometry of the tool? Is it the temperature of the roller? Is it the applied pressures and the contact force? So by knowing which one it is, we can actually optimize these processes and streamline them.
I have a bit of a different opinion on this. Maybe it's out of the ordinary, but I feel like this is an illusion for any complex system, certainly for the atmosphere and the climate system, where we have these physics-based models. But again, they're encrusted with these parameterizations that are essential and have thousands of tunable parameters. Those are black boxes. We comfort ourselves in saying, well, we're connected to Isaac Newton here. But at the end of the day, this is a black box that we don't understand the output. We can't write this down. We can't write the solution down on a piece of paper. So what do? We have to develop hypotheses, diagnostic frameworks to connect inputs to outputs, things that we can understand, and to a hierarchy, right? So we've got this super complicated thing we can't understand. We've got maybe some low order dynamics we can't understand. We need to build a bridge between those two. I think that's exactly what we're going to do with our machine learning models. And then we're going to expose their flaws in the fact that they're not obeying certain physical laws. But I think it's an illusion for complex systems, especially chaotic ones, that they're not black boxes. Any realistic one is.
Yeah, and just to finish some thoughts there, I kind of agree with Greg. We have the comfort of an interpretable model, but I think that works fine in many cases. But a lot of the systems we're talking about here, one of the things that we are not honest about from the physics side is that we typically don't even teach how to do multi-scale physics. What happens if you have a physics at a micro scale that talks to a mesoscale that talks to a macro scale? If you look at your entire educational structure, we always did uniscale physics. Consider the following equation. Then it makes sense to have an interpretable model. But when multiple levels of equations are talking, we currently have almost no mathematical skill set to model those dynamic systems. And this is why, Greg points out, we have to parameterize it. We feel comfortable like we have some model that we made up, but really we're curve fitting, just like the neural network is curve fitting, partly because we have this big gap in our educational structure around multi-scale physics. I think if we go to uniscale physics, having governing equations is what always has allowed us to make extrapolatory advances. So for instance, here's my iPhone. This was built by extrapolation, Maxwell's equations, quantum mechanics. So simple, we could walk it out and we eventually build a device like this. But when we get to something like weather and climate, I mean, this is so many scales in time and space. We just don't have good methods there. And until we do, I think ultimately the black box methods out of machine learning are going to actually win this one. It's already happening, right, Greg? I mean, DeepMind's already right there. And again, this kind of embarrassing, right? Here's a group at DeepMind who probably really haven't studied atmospheric sciences. They probably haven't taken very many science courses. I mean, mostly what I find, they come from computer science and they're like, science is this thing over there, but they come out of the gate and they can beat you at what you got your degree in and studied for too long in your life. And they just, oh, let me just get the data and watch this. I beat you. We have to deal with that reality. That is the reality we're facing, I think. Anyway.
I have more questions. What are the perspectives for making data-driven methods more failure-proof? Can we set limits on where more data only has a marginal effect on how reliable predictions become?
Anybody got thoughts on that one? I mean, I would just say that we need faster cross-validation techniques. How quickly can you cross-validate your models to like, it's working pretty well. I mean, there's always this issue of how much data do you do for test and training? You know, you usually say, oh, maybe I do an 80-20 split, but really it just depends on how much data you have and how, you know, you're at, you know, partly what's being asked here is how little data can I go down and still kind of feel like I cross-validated and I have a good model quickly, maybe. I mean, that's one way to think about it.
For reinforcement learning, it might be super important, right? I can't afford to do the models that NVIDIA and DeepMind has built. I don't have that compute. But if they open source the weights, which NVIDIA has done, then I can do some reinforcement learning relatively cost effectively on a limited data set and fine tune that for my applications. That's my optimistic view of how an extra bit of data we might be able to do something interesting.
I think an important consideration is when models diverge from what is actually happening, which can happen if sensors fail or there are new dynamics or something you're not observing is influencing the process. Like climate is always partially observed, for example. So in these cases, it's important to know where to sample to reduce uncertainty or error in your model. And randomizing data is one of the ways to do that. And also active learning, trying to sample spaces in your data that you haven't before. In RL, that would be like the exploration parameters in RL.
We going back to the very first question, and we will have this be the last question or a crack at this question too. Okay, so the original question was what techniques you believe are most effective in generating information from data, and the clarification is actionable information that can be used to make effective decisions. The agent can be either human or machine.
I mean, I'd say Krithika has some of that with her optimal sensor locations and optimal sensing. I don't know if you want to speak to that, but it feels to me like Krithika, that's the whole design of the optimal sensors is to extract that information really efficiently.
Yes, so those optimization objectives are connected to information theoretic criteria, but I think the deeper question is more related to not optimal sensing, but active learning. Where do you sample your data points and have you sampled enough of the distribution? And active learning gives you strategic ways to sample data from processes. So where do you simulate your next model? With what geometry or what initial conditions? That's where active learning can really play a role.
So in the weather world, people need to make decisions that have economic consequences and social consequences. And so they have a decision support system that has some inputs. So what we usually need to provide them with are these forecast inputs and their uncertainty. And that's really, that last part is key. If you have a cost loss function, you have some performance measure, you don't want deterministic inputs. You need to know the uncertainty because, you know, if you're a farmer and a frost is going to wipe out your entire crop, but there's a cost to mitigating it, you're more interested in what's the outlier solution here and how much does it cost for me to deal with that rather than say the expected value. So uncertainty, I think, is really key for that decision making.
All right, I'm gonna step back in here since we are at the 10:45 mark here in the Pacific time zone. This has been a great discussion. Thank you all so much for these fantastic insights and thoughts. on this topic. Excuse me. We are now going to do a short break for 15 minutes until 11 o'clock. So you can go wander the Whova platform and look at some virtual posters. And then at 11, we're going to come back in for our second panel, which will be on data, the path from a satellite to a scientist's computer. That's going to be moderated by Professor Alvar Sanz Otero here from UW. And so we will see you then. Thanks so much, everybody.
Thanks, everybody. See
Thanks,
ya.
guys.